right. So now I am happy to introduce Mina Sadayoshi from our Research Technology Data Services team. You probably know that as RIC, Research Informatics Center, who will be moderating the final series of presentations today. Mina, over
Thanks,
to you.
Dave. Yeah, so I'm a research data analyst at the Research Informatics Center, and I've interacted with many of you, many of the speakers as well as the attendees on your either office hours or a data vending project. So our speakers this afternoon have found creative ways to leverage STARR to create new value for their chosen projects. And they'll be sharing today how they've been able to make use of the vast repositories of data in STARR to bring new innovations for providers and patients. And our first speaker today is Dr. Shreya Shah. She's a clinical assistant professor of medicine and an associate medical director of the Stanford Healthcare AI Applied Research Team. And today she'll be presenting with three other collaborators, Adrian Lemaigre, Molly Strasser, and Antoine Vengrowski from the Codex Health Data Science team. They'll be talking about the risk and care gaps in AI approach for primary care. And just a reminder, if you have any questions during the talk, you can post them in the Q&A and we'll address them at the end. So Dr. Shah, excuse me.
No problem. Thank you so much, Mina. Hope you guys can see Molly's screen. We're really excited to share our project with you today. We've already heard such great applications of STARR over the last 2 days. So I'm part of the Stanford Healthcare AI Applied Research team. And the next slide has some information about what we do. Our expertise is really in partnering with data science partners to help evaluate AI technologies, including usability evaluations. The clinicians on our team are primary care providers. So that's the lens we're usually taking. The next slide shows our project team for this from the Stanford side, as well as our collaborators. And a little bit of background now. So one of the problems we were interested in solving was this issue that there are gaps in actually implementing guideline-directed therapy. Like, we know the guidelines exist, there's evidence to support that, but then there's big gaps in actually translating that in clinical practice. Combine that with rising healthcare costs. So what we're realized is there's an increasing focus on reporting quality and reducing unnecessary costs, and that there could be a great opportunity for AI predictive analytics to help identify patients at high risk of ED visits and hospitalizations. In the current state, this is actually a very time-intensive process that our teams undergo, relies heavily on retrospective claims data. One thing we're excited about is the idea that AI risk predictions that can proactively provide rising risk for patient populations is the potential's there, but we just haven't really seen any tools that provide kind of the whole picture of the patient. So what we've done is collaborated with Codex Health and Stanford RIT to develop a risk prediction tool to help with population health management informed by design thinking principles with clinical stakeholder input. The focus is really on facilitating adoption into clinical workflows and overcoming integration barriers. And after this tool is developed, we plan on evaluating the usability, feasibility, acceptability of it. I'm going to pass it over to the Codex team to talk a little bit more about how they leverage the STARR OMOP data set.
Hello, can you hear me? I'm going to take that as a yes. Yeah, so we're the data science team from Codex. So Codex is a company, just to give you a bit of background, that was founded in 2019. And our goal is to empower medical providers to deliver improved outcomes for their patients. Currently, we're designing tools and products to support two different kinds of care. One, as we're going to present on the population health side through the integration of EHR data. But we're also working on some remote patient monitoring solutions for the day-to-day management of chronic conditions, such as type 2 diabetes and hypertension. Just to give a little bit context, we're the data science team at Codex, and our role is to provide insights based on the patient's health data, both RPM and EHR based. So today specifically, we're going to talk about some different projects we've been working on with primary care data set, which is a subset of the STARR OMOP data set in collaboration with the heart team at Stanford. So quickly, we're going to talk about mostly two big projects. One, the prediction of ER risk based on EHR data, and then give you a bit of a demo on our tool for clinical decision support for the treatment and management of primary care conditions in primary care settings.
Thank you, Adrian. So yeah, hello everyone. Very excited to be here today. My name is Antoine, part of the Codex Health Data Science team. In the last 6 months, I've been working on this machine learning model to predict ER visits. And so this is what I'm going to tell you about. There's a lot of things to tell about a very short time, so I'm only going to focus on the essentials, but feel free to ask questions during the Q&A or after in private. So broadly speaking, the model takes as input 2 years of patient CHR and returns as a percentage a risk of ER visits or death in the year following the prediction date. When we take 2 years of patient CHR, what kind of information do we take? Well, pretty standard compared to what is out there in the literature. There's information on the demographics of the patient, visit history, biomarkers, drugs, diagnoses, and observation. Next slide, please. And I'd like to spend some time just detailing a bit the feature engineering and the feature exploration that I've worked on, especially because I believe that it can be of interest to other people here who are developing models. So there's been several improvements compared to typical practices that are done in the literature when developing a feature space for predictive model that we've done. And so those are illustrated by the 3 points that you see on this slide. The first point is that we've extended the look back time period to more than just one value. Typically in the literature, when people present predictive models, they use always a standard and always fixed period of time to look at their features. For instance, they will look at whether the patient has been prescribed a certain drug in the past year or not. They will look whether the patient has had a diagnosis in the past year or not. And it's always in the past year. Sometimes there's some variations, but we haven't seen a really deep exploration of this. So what we've decided is to extend the feature space so that each concept be analyzed through 4 time periods: the past 3 months, 6 months, 12 months, and 24 months. The second improvement that we've brought is a bit similar, the extension of the aggregation methods when considering biomarkers. So again, typically when considering biomarkers, so measurements like blood pressure, hemoglobin, BMI, most research would look at one method to aggregate those measurements. For instance, looking at the average BMI over the past year, or the last measured value of the BMI. We extended that not only to look at also the minimum value and maximum value, but also looking at trends and coefficient of variations, which are sometimes used, but for very specific measurements. Coefficient of variation, for instance, the only time I saw it used was in diabetes-related models and looking at the coefficient of variation of A1C. In our model, so we extended the feature space of measurements to include coefficient of variations to a greater corpus of measurements, leading us to realize, for instance, that the coefficient of variation of weight of the patient or of their blood pressure, the systolic blood pressure, turn out to be also significant predictors of future ER visits. Last but not least, we also, when dealing with measurement values, with biomarker values, rather than feeding the model the numerical value of this measurement, of this biomarker, we converted this numerical value into a category. So you have two examples here. For instance, a patient mean BMI in the past year is 28 kilograms per meter square. Rather than feeding the model this number 28, we converted it into the medically relevant category, so overweight. In case the value is not there, say there wasn't any measurement of BMI in the past year, rather than going through an imputation, we created a category no measurement. And so that allowed us to do two things to the model. The first is to inject an extra amount of medical information, of medical knowledge to the model, so that the model would know which values of BMI or hemoglobin or blood pressure to group together. This also allowed us to convey to the model that, for instance, hemoglobin for men is not, men don't have the same healthy range of values for hemoglobin as women, which is documented in the literature. So injecting all this extra medical knowledge increased the model's performance. Another thing that it helped do, I just mentioned imputation. Typically, models that use numerical value have a procedure to impute, to assign a value that is more or less arbitrary when the value is missing, which could create some noise and some falsehoods in the input. In our case, if we just tell the model that, if we create the category no measurement and we tell the model that there was no measurement, we do not create this noise, we do not create this falsehood. So this also led to improvement in performance. Next slide. Sorry. And yeah, so for those who know what ROC-AUC is, you can see the performance of our model on the left. For those of you who don't, you can just turn to the graph on the right, where we looked at the error between prediction and observed prevalence of ER visits. And so what we saw is that our model for a given prediction, say 79% for a given patient, 79% chances of visiting the ER in the coming year. The error for a confidence interval of 95% was plus or minus 2.2%, which we are pretty happy about. Next. And so the last is the caveats. So there are some problems still to be resolved. The first one being that the model, being a deep learning model, is black boxy. So it is impossible at the current time to assign reasons why this patient gets 39% of risk, whereas that patient gets 82. So this is going to be the work that we're going to be doing in the next few months. As well, there is a certain set of application for the model. In particular, we are focusing on patients with a certain set of chronic conditions. And last but not least, there is still a lot of potential in more feature engineering that we haven't explored. But yeah, we will leave that to future generations. So yeah, thank you.
Okay, so the next thing that we did with this data set was to develop a clinical decision support tool. For that, I'm actually going to give a demo because it's going to be slightly more interesting. And so here you can see the application that we developed. It's a tool that ingests the patient's OMOP data from the EHR and applies criteria and decision rules that we got from the relevant association's care guidelines, and applies them to identify gaps in the care that they're receiving. So this is what an example of what you'd see for a single patient. You see a little information about them at the top, their utilization and touch points with the healthcare system in the last 3 months. We actually surface that risk score that we're getting from the model that Antoine just talked about here on the left, as well as how that's evolved over time and how they look compared to the rest of the patients in the health system. An overview of basic labs and vitals, so that you can see a snapshot of where they are health-wise. And then this is the more interesting part that we just developed, which is the actual surfacing of recommendations based on care guidelines. So walking through this, you have the diagnosis relevant to the condition. And for all of these, if you hover over them, you can see the history of the diagnosis, procedure, guideline, lab. We have procedures that they've had that are relevant to this condition, studies and medications that are also driven by guidelines. And then finally, over here on the right, the recommendations. So after applying the different criteria that drive the guidelines, we've identified where patients could potentially benefit from changes in cares or additions of medications or perhaps procedures. So you'll see the recommendation surfaced here, like consider adding digoxin. And then you might think like, why is that? So if you hover over the question mark, we actually have it linked to where it exists in the association's guidelines, as well as a more detailed explanation and a level of evidence. And so we do that for medication studies and procedures for each patient. So that was what the other project that we did with this data set. Now back to this.
Yep. So back. So we had planned to speak a bit about the different things that worked well and different challenges we met while using OMOP in general. But since we're running a bit out of behind on time, I'm just going to skip a bit and focus on the main challenge that we faced, which was the requirement of having domain knowledge into 3 different fields. First, in the technical knowledge, so knowing the different technologies, tools, and libraries needed to work with SQL, OMOP, and OMOP data and produce machine learning models. So this was mostly this was mostly knowledge that the DS team had prior to this work. We also required, obviously, medical knowledge to actually understand the data we're looking at and make sense of the results. And for this, we relied a lot on the collaboration with the HART team at Stanford. So thank you very much. And and we also required a lot of ETL knowledge to understand where the data comes from, what are the limitations, and to really understand the context and how the data set was built. And for that, we had a lot of back and forth with our IT team here at Stanford, in particular Priya. So thank you very much for all the support. Now we will be taking questions if you have any.
Yeah, I don't. Thank you very much, Antoine, or Adrian, and Antoine, and Shreya, and Molly. I don't see any questions currently on the Q&A list, but are there any that are coming forth?
It was really cool to see the app. So thanks for showing it.
Yeah, I guess I'm curious because I think I did work on a heart failure dashboard thing. And I know I don't believe we were using the OMOP data, but the intent for this is eventually for it to be part of the care, right? So have you been looking at getting the data feed from Epic as well, rather than the OMOP data?
Yes, actually, we're building our own ETL based on EHR integration using the FHIR HL7 format, which is our end goal. The big reliance we had on OMOP is the whole mapping to concept IDs and ancestry, which has been invaluable at building cohort, building features, looking for the required relevant fields and medical concepts, and is something we hope to port from OMOP. We're also very likely going to be relying on the vocabulary tables and the concept ancestry tables built by Odyssey for all these EHR-based products.
Do you have a sense of how the OMOP data lines up with the EHR ontology and things like that?
It's still a bit complicated for now. We know that in the EHR, because of the identification processes, we'll get a lot more data. There's some data that we don't have in OMOP currently that we would be getting from fire data. And also OMOP conveniently provides a lot of structured information, or at least a lot of the information in a structured format. And a lot of that structuring work that is currently being handled by the Stanford ETL will have to be done in-house, in particular mapping the different concepts and medical vocabularies used in fire to their counterpart in OMOP, which OMOP handles semi-automatically for some concept, but not necessarily for everything.
Yeah. Great, very exciting. Thank you. Thank you to all of you. So our next speaker is Catherine Connors, and she is the Associate Director, Research Participant Engagement Program in Translational Research Operations. And as such, she's passionate about engaging diverse patient populations and communities in research. And her talk today is titled Supporting Research Participant Engagement Using STARR. So Catherine.
All right. Hi,
Excited.
everyone. Thank you. Are you seeing my screen okay? Okay, great. So I think I might help us catch up on time a bit, since rather than going in depth on a particular project, I'm really giving an overview about our program and particularly how our participant engagement platform integrated with STARR can support your research through engaging participants. So we're largely funded by the CTSA award under Ruth O'Hara. And my slide's not changing, sorry. There we go. So those of you involved in participant recruitment know how challenging it can be. It's one of the biggest challenges to successful clinical research. And Stanford has needed some tools to help scale while protecting patient privacy and data security. And we also want to really address the lack of diversity and inclusion in trials. So with that, we, myself and two other team members, we make up the participant engagement program. We meet with study teams regularly, 2 to 3 times a week. It's about our current rate. And we do tend to focus on our participant engagement platform, PEP, also known as our Honest Broker Control Center. And I'll go into that a little bit more detail. And the channels that we offer, the outreach channels we offer are direct email, Children's Epic, MyChart, postal mail, and then last fall we launched the SHC Epic on the adult side, MyHealth, the MyChart equivalent on the adult side, which was badly needed. So we're really excited about that. And beyond Stanford, we have social media resources and a research registry that's in RedCap that's mostly focused beyond Stanford, Bay Area, but also goes beyond that. We keep community engagement in mind whenever it can be applicable. And we offer guidance about other resources. One of my team members is the Hub Liaison member for the CTSA Trial Innovation Network, which helps support multi-site research. And she actually is also using STARR on a regular basis for feasibility analysis to see if we're, when we're vetted to be a participating site for a study. So real quick definition on what is Honest Broker. It's a term we use a lot to differentiate between what we can offer versus typical participant outreach strategies. So current PI physician contact, physician referrals, the colleague networks, the clinic visit itself, flyers, and community events moving more beyond. And so those first few are great for promoting the patient-provider relationship, which is very important to leverage whenever possible. But the downside of this is how time-intensive this can be for study teams and physicians. It's not as scalable and it may not be applicable. So if you're trying to reach patients that are not within your clinic, you could be a little bit stuck unless you can work through provider referrals. So enter Honest Broker, which is basically a role served by my team. We are conducting the outreach on behalf of the study team. Only when participants or potential participants express interest in a study are they connected with the study team. And so this is really great from a privacy and compliance standpoint. And then most exciting to us is how scalable it is. We're able to reach more people and give them the opportunity to participate in research. The downside we want to keep in mind is that it's not leveraging a treating relationship if it's there. These invitations are coming from us, which, you know, the patient does not know. They'll recognize Stanford Medicine name, of course. Okay. Quick overview of how our consults work. So this is the information that we'll collect. This onboarding capacity, number of potential participants a study team can screen and schedule in 24 to 48 hours. That's important when PEP is pulling from STARR, that we build a wave that's not going to be too big or too small. I mean, we figure it out as we go. The first wave is our test. And of note, PEP is integrated with Encore, our clinical research management system. And we do require per participant accrual versus the summary accrual option. And this ensures that, well, I'm going to go into more detail, but that PEP doesn't send invitations to patients who are already enrolled per Encore. Also, PEP is ensuring opt-outs are followed. So in these consultations, we'll provide detailed IRB guidance. We'll guide the team if needed, if they need our assistance through building their STARR cohort based on their study inclusion/exclusion criteria. And if it's for MyChart or MyHealth, we make sure they have their study registered in Epic. So familiar screen right here. This is a standard slide I just review with our study teams to make sure that they're aware of the great resources through STARR. So as you know, anyone with a SUNET ID can just go in and play with the cohort discovery to get some counts, pre-IRB, de-identified data. Now study teams can go through the chart review process with IRB privacy approvals and get this great list of potential participants, but they might be stuck in actually they can't cold contact these patients if they're not within the treating relationship of the PI. Again, so that's where Honest Broker can be a big help. I put the little asterisk there just because there are like provider referrals as a possibility. Those can also be logistically challenging. But we do offer templates to support that if it's a good fit for the study team. So essentially, we as Honest Broker are doing the chart review part on behalf of the study team. So to quickly recap, so PEP is identifying these potential participants based on a STARR input. Like we download from STARR the patient listing, the chart review. And then PEP, think of it as a control center built by our colleagues in TDS, slices that patient list according to the contact they have available. So if they have a MyChart, MyHealth account, that's going to be prioritized. If direct email works for their study, that only works if healthy volunteers are included. That means that when we send that invitation, we're not implying that they have a particular condition, which would be the HIPAA violation. So direct email works when healthy volunteers are included. And we also have postal mail, which remains, even though we have both secure portals launched, postal mail remains an important option for those condition-only studies that want to reach patients that don't have a MyChart, MyHealth account. So within the same study, you can use multiple channels, all coordinated by PEP. So we serve as the Honest Broker, and then PEP is tracking age, race, and sex metrics. And so prospectively, we can modify outreach to increase representation of underrepresented populations. Many of you probably already know about this. On both hospitals, there's this We Ask Because We Care campaign. The phase 1 race, ethnicity, preferred language has been completed, and now the SOGI, sexual orientation and gender identity phase is going on now. And if you've seen the updated list for race, ethnicity, and language, it's really comprehensive and inclusive. And so basically patients are being invited to update their demographics. Super exciting for us because the data that we pull, just like all of us, from STARR, from from the Epic systems, it's only as good as what's in the EMRs. So to have this better demographic data is really exciting for us. And then via STARR, PEP will be pulling this new data in. It'll take a while for the updates to take place, but we're really excited that this is happening. And we're currently, our TDS colleagues are working on this new PEP feature we call demographic optimization. This is going to be where we can actually work with the study team to input desired demographic targets. And then PEP will automatically, from the STARR poll, continue to prioritize those underrepresented populations until that enrollment goal is met. So this is our current, it's the very basic, not super thorough race, ethnicity, sex data. And then in subsequent phases, we'll update this. We have plans to do age ranges, pregnancy status, disabilities, SOGI, and the comprehensive racial breakdown that's being carried out through that campaign I just mentioned. Okay, this is kind of a summary slide. So our PEP honest broker services, again, those are Stanford patients. It is completely relying on STARR polls to create the listings. And then our beyond Stanford services we offer as well. And you can see how we launched on the children's side quite a bit earlier than the adult side, and that will show a bit in our data. Okay. This is a quick workflow from left to right with our process. So you'll see the STARR cohort pulling here. And then right after this step, so PEP is pulling the cohort from STARR, validating that the study is open to accrual in Encore, as I mentioned, screening against those on-study participants per Encore, so we don't send them an invitation when they're already on study, and making sure that we follow our opt-out list. So we have quite a low unsubscribed list, but that is tracked via PEP. PEP is identifying the best outreach channel across our services here and generates a system-friendly listing. So right now for direct email, for example, we're using Qualtrics, so the listing can be imported into Qualtrics. Similarly, it generates a postal mail listing. And it's tracking the outreach progress for our studies, which flows into Tableau reporting. This is way too busy, but I just wanted to highlight a couple things that, so yellow is Rick, Research Informatics Center running STARR, which this box, I need to really color code white and yellow. But essentially white is study team, yellow is Rick, and purple is our team. This is just sort of green means go and red means stop. And so this left-hand column is, study team wants to access patient data. This is essentially the cohort discovery and chart review workflow done by the study team. But if you want to contact patients, that's where you might want to consider a consult with us. And then just to summarize participant contact options. The PI can contact their own patients. You could contact patients through providers, and we offer a template for that. And then this purple area is essentially our participant engagement platform, that is pulling from STARR. And I go into detail the IRB and STARR steps here for the different channels. And then everything is flowing into Encore, and this data flows back to PEP for our metrics. All right, I'm pretty much wrapping up here. Just some quick summaries. So we've done 173 consults for teams to date since we started logging this in 2019. Because we've started early on with children's, with good support for research there, that's really the majority of our studies, but we're starting to become more evenly split across our different services. Epic My Health again launched quite recently, so that will be starting to spike more. Study Pages is a study directory landing page, and you can integrate it with social media. It has nice participant tracking and text messaging, another resource that we offer. And quick summary. So let's see what to highlight here. So you see these are essentially our PEP honest broker channels. And this data is from March, 45 studies. We've outreached, this number is more like 170, 180,000 right now. And across all channels, we're averaging a 2.4% interest rate. And that, translates to 3,000 patients that probably wouldn't have heard about the study without our outreach. We have this wide interest range, the rate range here, really depending on the study. And this is just some comparisons with our research registry and study pages. We've launched a fee-for-service model just to subsidize our efforts. We launched that in the fall for the services we have available. So I have the link here. I also have a how to plan a recruitment budget template, because one thing we've realized is we really need to try to catch study teams pre-grant, let's say, rather than when they more often come to us when they really need, a little bit more desperate help with recruitment. We want to be more proactive in planning the recruitment strategy and the budget. And that is all. I will check the chat for Q&A. Thank you so much. I'm happy to answer any questions.
Yeah, great. Thanks, Catherine. I know this comes up a lot in our office hours at RIC. We have a question from Paul Tang. To leverage the physician-patient relationship, could physicians voluntarily endorse your program?
Ooh, could you expand on that a little bit more in terms of like how that endorsement might work?
Maybe we can take this offline.
Yeah, I think he's looking for a way to I don't know, direct patients to you, or like support for.
Right.
Yeah. But I don't have more information than what
leverage the patient relationship could. I mean, so Stanford is sorry, my dog is barking in the background there. So Stanford is what's called an opt-out institution technically, which means all patients that come to Stanford may be approached for research unless they opt out. And that actually doesn't mean a global opt-out. You could opt out from hearing from us, the Honest Broker program, but we can't guarantee that someone else won't approach them for research. Mm-hmm. So when physicians voluntarily endorse our program, I'm thinking that it would be awesome if physicians encourage, this is not really related to STARR, but if physicians, patients could sign up for our research registry, which is an opt-in versus the opt-out. So if that's kind of where I'm thinking like the opt-in part of it would be relevant, because otherwise any patient may be invited by us. Once they get their first invitation from us, they have the opportunity to say, hey, I don't want these invitations. May not have really answered the question.
He did provide some more context. It was one of your cons. If you have patients eligible for a study that a physician actively endorses, could you put the MD's name on it to help with trust?
Oh, yes, exactly. Okay, thank you. Yeah, so we have what I call a provider PI co-invitation template. And that would basically, you'd go through the STARR chart review process to access the providers of the patients you want to reach. And then you would basically have the endorsement for those providers to put their name on your co-invitation.
Okay, great. Thank you so much. So we're going to move on to the next talk. Thank you very much, Catherine. Sorry. We need to keep things moving with Jason Fries. Dr. Jason Fries now is a staff research scientist in the Shaw Lab and a research consultant at Snorkel AI. His research focuses on weekly supervised machine learning training, foundation models for medicine, and methods for data-centric AI. His aim is to enable domain experts to rapidly build and modify machine learning models, and he'll be presenting today on Lumia, a generative language model for the EHR text and codes. So Dr. Fries, welcome.
Hey, can you guys hear me? Hopefully.
Yeah.
Hey, great. I'm going to share my screen. Go for that. All right. Windows open. All right. Begin. Oh.
I apologize. I just realized, I think Mike Van Ness was supposed to present.
Oh, should I bomb out? I'm happy to defer to Mike if he's on a schedule.
I'm happy to go next. I mean, you're already sharing. We could just
okay. Let's keep going.
That's fine.
Okay.
I have my apology.
Sure.
Thank you.
No,
No, it's all
worries.
good.
Can you guys see the slides okay? I don't seem to.
Yeah, we can see a whole screen. Is that?
Yeah, I don't know why it's not, maybe this. How about now? There we go.
Yeah.
Okay, perfect. All right. So thanks everybody. So to sort of start this conversation, I'll back up to my original opening slide. Yeah, so today we're going to talk about Lumia, a generative language model for EHR text and codes. This is really apt considering our moment where in the past 6 months or so, generative AI has really broken into the mainstream. And it's excited a lot of people about the opportunity to use this technology in medicine. And it also has raised some legitimate concerns about the safety and behavior of these models, and they're prone to hallucinations and making up information. So there are lots of legitimate technical questions and to sort out before we imagine using these for patient care. And so language models are actually a more general class of ML tools that have started to really come into their own in the past couple of years, called foundation models, a term coined here on campus out of Percy Liang's lab. And it's this idea of building a often large, extremely generalized foundational component of an ML system, and then using that foundation to rapidly adapt to a very wide range of downstream tasks. And the way this works is leveraging a technology called self-supervision or self-supervised learning, in which we often can formulate any or many types of data as a sort of language. And then we can define an objective for a machine learning model to learn to predict that language. And this gives us these very powerful models when we can expose them to a lot of training data. And so while this has been going on and all these big successes with OpenAI and ChatGPT, what we're really seeing is this other trend emerging at a really astonishing pace of language models becoming smaller, more accessible, and generally commodified. We have great researchers on campus in the CS department who are replicating the original GPT-3 model now for $600. There's a leaked memo out of Google that highlights how none of the big tech companies have an AI moat. The open source community and sort of the data owners are moving so quickly that that's no longer really the moat to protect innovation. And stances like OpenAI of having secret private models really aren't amenable to the kinds of guarantees and transparency we want in medicine. And so we in the Shaw Lab, myself, Nigam, and a bunch of students have written a number of pieces, blog posts and papers about thinking about how this new class of foundation model, could change, improve, and be utilized in medicine, including understanding different ways to evaluate success and different properties that you want to be desirable in these models you make. And, as we've done a bunch of evaluation on sort of current state of the art, what we've seen is there are two kind of worldviews that are dominant in medical machine learning. We have on one hand, the natural language processing world. Those are models that really operate over clinical documents for information extraction, finding relevant facts to incorporate into other modeling or phenotyping applications. And then we have another world of models that are built on codes. This would be the type of SNOMED, ICD codes that are populated in STARR OMOP. They give you nice compressed information about the longitudinal record of a patient's history, and they provide a very powerful source of training data for building a bunch of clinical predictive models. If you look at how these two things are evaluated, though, they're very different in terms of sort of a lens of reproducibility and extensibility, which is to say that in the NLP world, a lot of these models are trained and made available to researchers, which enables them to some degree replicate results or at least understand the performance of models in a more transparent way. For models trained on medical codes, these are often very private. and not shared the larger research community. And as a result, we never really get to benchmark or understand how these models can be used and transform key aspects of healthcare AI. And so it really is hard to take this holistic view, quote unquote, borrowed from Percy Liang's lab, and how we should think about evaluating AI and ML in the future. And it really makes it hard to assess utility and usefulness in clinical settings when we are always comparing apples to oranges across different deployed settings. And so this leads to our research into EMR foundation models. Yesterday, one of NIGM students, Ethan Steinberg, presented on his work in motor. This really uses this fantastic idea of self-supervision and the availability of data made possible through STARR OMOP to train a large-scale foundation model using all of Stanford data. And the basic idea here is you take STARR OMOP, you transform it into a certain type of representation, and you train a machine learning model over everyone, all the 3.8 or so million patients and their timelines in Stanford. You can actually train larger on data sets like Truven. They contain 70 million patients. So you can train these extremely large data sets and arrive at a pre-trained model, which then can be rapidly adapted to downstream, classification tasks of interest, which is, where most researchers actually live in their day-to-day. They have an expert area they want to focus on. And this works because of this idea of what's called transfer learning and this ability to share structure across problems. And it's really opens up this huge class of powerful models. The key insight into how it works is that we view OMOP data or any medical ontology data as a form of a language, like I sort of opened up with. And we just use these kind of CS tools for pre-training to define a way to learn that language. In this case, learn the language of EHR medical codes in time. And, I won't go into the technical nuggets here, but basically this gives you a mechanism by which you can be given a feature representation of a patient at any point in time and in their, in their timeline. And this then gives you a very compact and powerful representation to use in a variety of downstream classification problems. So the issue is that we've done a lot of work in our lab with coded based foundation models. On the left here, we've benchmarked these things. They give you overall performance improvements over state of the art like XGBoost by consistent numbers, 1 to 2 AURC points or more. They are more robust to temporal shifts. So if you can train a model and it lasts for longer without its performance decaying, and it dramatically changes the trade-off space of how much labeled data you need to build a model to begin with. So as Ethan hopefully touched on yesterday, in his work, he's finding you can train data models using 95% less data and still match state-of-the-art performance. This is an idea gets to an idea called few-shot learning, which is can we learn to do more with less and sort of use a few examples to build models more quickly and then sort of interrogate and prototype more rapidly. The trade-off with codes is that they're incredibly opaque and unintuitive for anyone who's ever tried to look at them or understand what they actually map to. So, we'd want to maybe imagine a universe where doctors could interact using natural language and sort of describe things more about interacting with notes or the type of patients they want to see or the outcomes they're interested in, and use that really flexible interface to more rapidly build new models or define what are called instructions. Those are just rules to follow for building new classifiers or phenotyping and those kinds of things. Unfortunately, there are really no open, large clinical language models that have seen the scale of data required to perform well, the scale of EHR data, and have the certain architectural properties to be used in these ways. And so all of this has been the motivation for Illumia, which is a language model for, it's a backronym actually generated by ChatGPT, but it's a language understanding for medical insights and action. in which we train on not only all of the coded data of STARR, but all of the patient notes organized into a timeline and used to train a large, in this case, up to 2.6 billion parameter language model from scratch, and then adapt an incredibly powerful off-the-shelf model of the 7 billion parameter size, which is more akin to what you see with ChatGPT. This is done in collaboration with the Centers for Research and Foundation Models and CS, that's headed by Percy Lang and a bunch of other folks. And our question is, how can we combine a bunch of rich modalities, both text from notes or flow sheets and medical codes, in a way that we can both have a model that uses both of those, but also potentially interact in the shared interface of language. And so the kind of trick here is that we just really represent everything as text. We take these timelines and create a very light markup. We use a sort of version of XML, but you could imagine doing this in Fire. The gist is it gives you a structured representation of every event in order that has occurred in a patient's journey through the hospital or healthcare system. What's critical to this, and what is one of the key sort of innovative pieces on our end, is that when you add everything, you blow up what's called a patient context window. And these models can only look at so much data before they run out of memory. If you were to pull an off-the-shelf clinical BERT model, for example, they can only capture 18% of a patient's notes. And if you were to look at everything, including codes, they can only capture 4% of patients. And so Lumia is more in the 50 to 60% range and able to actually ingest in one go everything that's occurred in a patient's timeline, including notes. And this is done in a way that includes markup, so that in principle, you can interact with this timeline data in a way that looks more like how you might interact with something in ChatGPT, where you can talk about a patient's history or ask for particular parts of a patient's record, but have that silently pulled in behind the scenes to be available to answer questions and do a bunch of other critical information seeking tasks. And build more powerful predictive models, hopefully, since we can see both notes and codes together, and notes capture stuff that often isn't coded. And our goal here is to both train this model, but hopefully make it available for researcher use, at least starting in Stanford, to help accelerate innovation into new clinical use cases for large language models and prompting more generally. And so we're also releasing this as part of a big benchmark suite of sort of standard stuff you can play out, so that future language models will have to have a shared common language of how they perform. And we're also working closely with clinical collaborators to come up with new tasks that are different than the sort of classic NLP stuff that often does not really translate to the types of things you do in the clinic. So that all sounds great. As anyone who's ever trained these models go, they are massive engineering and computational enterprises. So we've built all of this stuff to train the model, and the model now is training. And so you'll have to stay tuned for us running our evaluation suite next week to actually get numbers. But we're very positive in sort of the preliminary stuff we've seen that this will provide a really powerful tool to share with researchers. And so this is a huge effort. Dozens of people even not on this list have been involved. And so I'd like to thank all the collaborators for helping this big team science effort. And with that, I'll open it to questions. So thank you so much.
Great, thank you, Jason. We do have one question. It was not on the Q&A, it was put on the chat, so I can see it. It says, what about Gatortron as a large clinical language model trained on the University of Florida's complete corpus of clinical notes? And then there's a link put in here.
Yeah, Gatortron, that's a great point. Gatortron was trained internally on a large collection of notes. However, that model was not released. They released a much smaller model, and it is what's called a narrow technical nugget. It's what's called a masked language model, not an autoregressive chat style model. So it has sort of technical limitations in what you can do with it. It would be great if NVIDIA released the large model, which should presumably have some interesting performance characteristics, but they have elected not to for, whatever reason. So that's really why I think, if we want innovation to scale up, we need to make these available to researchers to interrogate how these models actually perform in a wide range of tasks.
There's another question here in terms of number tokens. How big is the context window in Lumia?
Yeah, Lumia, this first version is 4096. We are planning on training the new MPT model out of Mosaic, if you're familiar with that. That uses some twists to allow some extrapolation to much longer context widths. So we're very curious about how that will shake out in practice when our timelines in the most extreme case are often over 32,000 tokens in length.
Right. Okay, another question from Nima Agayipur. What are, great talk. What are some of the clinical use cases that you are considering?
Yeah, that's a great question. So a lot of what we've been working on is sort of, a lot of sort of, populate a note for me based on current history, or draft a note for me. Like, could you draft a progress note? Could you generate a discharge summary given all of the patient's history? Could you propose a draft there for that? Another thing is a lot of information need, right? Like, you may have a patient come in and present to you for the first time, and you may have to do this sort of soul-sucking slog through the record to find all the information you need to actually make care decisions. And so we're building a bunch of evaluation tasks around those kinds of information needs. So you could just sort of quickly summarize this, what did the last referral look like? What did that doctor recommend be done with this patient? Those types of things that would normally be very manual, but hopefully we can accelerate.
This is my question. So I've noticed, there's a lot of holes in the EHR. There are incorrect, codes and stuff like that. Is that something this would be able to address it?
Yeah, that's a great point. And it's something that we're really excited about that we haven't measured, but that Climber especially seems way more robust to errors, which is to say codes that are missing, codes that are assigned incorrectly. And it seems like that even in a presence of much higher noise than you'd expect, it can still be used for a bunch of downstream tasks without introducing error. I say that as a qualitative, not formally measured yet, but a promising direction. So
cool, great, thank you. Thank you so much. So let's move back to Mike Van Ness now. So I apologize, Mike, for skipping over you. Mike is a PhD student in the Department of Management Science and Engineering, and his primary research focus is addressing problems related to missing values in tabular data with application in healthcare. And he's speaking to us today on using STARR OMOP and Atlas for interpretable heart failure prediction. Thank you. Mike.
Thanks for the introduction. Can you guys hear me and see the slides? No problem. Yeah. Okay. So I'm a PhD student in management science and engineering, and I've only recently kind of begun to really dig into doing research related to this STARR data, and it's been very exciting, and I've gotten lots of great help from lots of people from the STARR team. So really cool that I'm now able to come here and tell you all about it. Before I get started, just quickly wanted to mention the people I've been working with. My primary PI is Madeline Udell, and I've also worked a lot with another PhD student, Thomas Buschüther, on this project. And then from the medical side of things, we've primarily been in contact with Alex Sandhu, who's a doctor associated with Stanford Medical, and also Natasha Din, who is associated with the VA and also Stanford. And then Alex has worked with Andrew Ambrosi, who works at Kaiser. And Alex and Andrew work primarily on cardiac research, which is where this application in heart failure, I guess, originally came from. So I think to set the scene a little bit about how this all kind of came about and why we became interested in this. So Alex and Andrew have been working on a grant proposal, which they have recently submitted, I believe, to do better prediction models for incident heart failure. And when they were seeking, I guess, more like data science help with their proposal, they came to us, and in their presentation, they presented us with this paper, which had this table in it that I show on the left over here. And their claim was this was a typical model that is being used in the medical context for doing something like heart failure risk prediction. And as you can see, the table has a list of a reasonable number of covariates, and it has coefficients here, which represent the coefficients for a fitted Cox model. And their, kind of overarching question was, well, can we do better incident heart failure prediction with all of the data that's available, starting at Stanford, and then if it's successful at Stanford, even moving to VA and Kaiser data as well. And so, the first question was like, okay, so like, what are the limitations of, what are the limitations right now of what's being used? And, when we were looking at this, I guess the first thing is that, well, it's a Cox model. So it's this linear model that assumes proportional hazards. And we think we can probably do better than this, but we have to think a little bit about how to do that. And secondly, it doesn't use any historical data in this table over here. You're just taking measurements from patients when they arrive to the hospital, and you're using just that to make a prediction about the risk for heart failure, and not using any historical data you might have about patients. And third, and maybe more importantly, is that a lot of the models like this, these Cox models that are used in practice, are not really trained at scale. And so, this was kind of the motivation for, can we build a better model for heart failure using, data from STARR OMOP? So I guess mostly what I'll do is kind of walk through how I went about, I and the rest of the team went about building this model. And yeah. So I guess the first step in doing this was identifying a cohort. And I was pretty new to these tools. So I was, very thankful to, get a lot of support from people and like figuring out how to establish a cohort. And pretty quickly, I was kind of steered towards using Atlas as a pretty decent tool. And I was pretty satisfied with the results of being able to use Atlas, because once I was kind of nudged in the right direction, it was pretty easy to figure out, I guess, establish like a pretty simple setting for like how to build a cohort and then how to like generate that cohort. So I have a screenshot of that here. And I guess the best part about using Atlas, at least for the use case that I was doing, is that it was very easy to then go from Atlas to then actually gathering the data. Well, I shouldn't say really easy, but once I was able to figure it out, it became very easy. So, as you can see here in this top left screenshot that I have here, these were following a lot of the tutorials that are available on GitLab from the STARR research team. You can just go to Atlas and export BigQuery SQL directly after you've defined an Atlas cohort. And then once you do this, then I've attached this snippet of Python code down here, which you can use something like this to then take your BigQuery SQL and connect this to a Google Cloud project and very easily download your cohort that you've created in Atlas. So this is what I did. And once I had the raw data, then it was a question of generating features. And I ended up using this very nice package called PyHealth, which has a lot of tools in place for pre-processing data in the OMOP CDM, which was very useful. And I was able to build a lot of code on top of that. I found this actually to be more useful for my application than using some of like the Odyssey tools, like the feature extraction or patient level prediction package. I'm happy to talk about that more, but the TLDR is that the Python code I thought was more malleable, and I was able to better edit it and build on top of it for doing such a methodological paper. Anyway, so after generating features, we ended up with the cohort that I've described here on the right hand side. We ended up with quite a few number of patients. We ended up with over 350,000 patients and close to 1,600 features. And these features represent a lot of measurement features and also conditions, drugs, and a few demographic features. And it's worth noting that of these measurement features, a lot of them come from, the reason there's so many of them is because we have historical data for our patients. And so we generate, I guess, like feature engineered measurement covariates from this historical data. So like mean, min, max, standard deviation, things like this. And so this is why we end up with a lot of measurement features. We end up doing feature selection on this later. But so I'm actually not really going to talk. I don't have much time today, so I'm not going to talk really about the methodology that we use because I think it's less interesting than just showing some of the results that we got. And what I will say though is that when we were trying to build models that are better than Cox models, we also wanted to make sure that we were limiting ourselves to models that were highly interpretable. And we thought that was very important because we wanted to, develop models that actually have a chance to yield interesting insights and be trusted from a medical audience. And, so the long and short of it is we were able to develop this survival analysis pipeline that was able to generate these nice plots like this. And these are some examples of results that we ended up getting from our study. And these single plots over here are examples of individual shape functions. So the model we ended up fitting was a generalized additive model of sorts. And so each of these functions, I guess, is the individual contribution of each feature towards the downstream hazard function of the survival analysis problem. And if this was a Cox model, of course, then each of these plots would just be a single line because it would be a linear model. But because we're using a highly nonlinear model, we are able to get, I guess, more nuanced shape functions. And so you can see, some very unsurprising results, such that as you get older, your risk for heart failure increases. And then this max creatinine level, measure of kidney function, also as the creatinine increases, your risk of heart failure increases. One, I think, really interesting result that we got was our model also allows for these interaction terms. And these interaction terms can be quite interesting. So in this case, what this interaction term is saying is that after accounting for the effective age and accounting for the effective QRS duration, which is a measure of heart function, after you account for those separately, then the interaction term says that if you're young and you have a slow pumping heart in terms of QRS duration, then that's like an additional risk of heart failure beyond the individual terms separately. So that's kind of like the big level of how we went from an idea for building a model for heart failure to an interpretable yet accurate model. Of course, I didn't go into a lot of the technical details, so if anyone has any questions, then please let me know. Happy to take some questions now or offline or whatever.
Yeah, thanks, Mike. That was really good application of the STARR data and the atlas. Unfortunately, because of our time limitations, I am going to have to ask people to contact you offline. But thank you very much for your talk. We're going to move on to Daniel. Now, Dr. Daniel Tawfik is an assistant professor of pediatric care, critical care medicine. His lab's mission is to identify aspects of the healthcare system that enable high quality care and provider well-being. And he'll be sharing today about using audit logs and STARR to predict physician burnout.
All right. Hi, thank you, Mina, for that introduction. And I will do my best to keep this brief, but yes, also happy to take questions afterwards or offline. And I just wanted to highlight just some of the work that we're doing using STARR to kind of approximate EHR use or quantify EHR use in predicting physician burnout. So just by way of background, we're focusing on primary care physicians. About 1 in 3 physicians in the country is a primary care physician. And burnout is quite prevalent among primary care, anywhere from about 40% of physicians, or more recently during the COVID pandemic, up to 2/3 of physicians. And one of the key limitations with evaluating burnout is that it's always retrospective, and you're always evaluating it based on survey responses that are based on what people have already experienced. And by the time you evaluate those surveys, sometimes whatever those stressors have been are way down the line. Sorry, is my microphone not picking up well? Let me try something. Let's see if that's better. I'll try to talk loudly. Sometimes this mic doesn't pick up very well. So the issue with burnout is that it's always retrospective because it's based on survey results. And so even though we would like to have this nice clear picture of the road ahead and what can we do to prevent burnout or kind of improve the situation of physicians, really we're just looking in the rear view mirror because it's always retrospective. So the goal of this project is to develop ways to identify those areas of the healthcare system that are putting physicians at risk for burnout, so that we can actually intervene prior to it becoming a problem. And so what we've done is we have taken burnout scores. So these are survey results in UHA or University Medical Partners. They send these out yearly. WellMD sends them out to the School of Medicine about every year and a half. And we link those to EHR usage data. And so one of these sources is signal data. So Epic compiles signal data on a monthly basis, really kind of summarizing, how much time people are spending in various aspects of the EHR, how customized their EHR is, how big of a workload they have, et cetera. And we actually layered that with data from the de-identified version of STARR OMOP. And since we're really focused on the physicians, we didn't need any patient identifiers, and so it actually worked out really nicely to not have patient identifiers in there, or have it set up in that way. And we were able to look at the notes and kind of do some analysis of the length of notes, some of the content of the progress notes, and some other workload metrics. And then the future step, kind of an ongoing step, is then adding in even more detailed data from the raw audit logs, the timestamped actions from when people are interacting with the EHR. And so what we've done with those, once we had that linked database, our primary algorithm was based on gradient boosted model, although we did also look at logistic regression, random forest, neural network, and k-nearest neighbors as other candidate algorithms. Did this kind of nested cross-validation. And so, with an 80-20 train test split, with our 80% training set, did a threefold cross-validation that we used to find the hyperparameters for the chosen algorithm. The hyperparameters that maximized the AUC across those three folds, then trained using those hyperparameters, and then reported the test findings from the test set. Because this train test split can be pretty variable, we had a fairly small data set as far as these approaches go. We actually then iterated this whole approach 40 different times using a random split each time. And so a person may be in several of those 40 folds, either in the train set or the test set. And so what we found, we have individuals from 93 different primary care clinics. So this is about 414 physicians. Across a 2-year span, they filled out almost 700 wellness surveys. And one of the interesting things we were able to do is then link those physicians to the notes that they wrote in the months leading up to each survey administration. And then from those notes, we're able to do some, compared to what we've seen today, some very rudimentary analyses, but just looking at kind of sentiment analysis, subjectivity of the notes, the changes in these over time, as well as some other markers such as typos in the notes, length of notes, number of various types of notes. We're able to search for keywords or key phrases that have been shown to be associated with burnout. And then we're able to link that to the rest of the EHR usage data. The burnout data that we have for these physicians was fairly well distributed. These are the 3 different service areas. It's either SHC, Stanford Children's Health, or University Medical Partners, because this is aggressively de-identified, to say the least. I can't actually tell you which service area is which, although they did appear to be fairly well distributed. Same thing for specialties. We had 6 different primarily outpatient specialties represented, all with fairly similar burnout scores. We did have more women physicians than men physicians, and they did have higher burnout scores on average, which is consistent with the prior literature. But then when we did the prediction modeling step, what we found was, kind of, marginally good performance. The gradient boosted model and the logistic regression models overall performed the best, particularly in this kind of minimizing the false negative or maximizing the true positive section of the curve, which is kind of our most important area that we're focusing on. Whereas neural network and reinforced didn't do quite as well, especially in that. When we look at our top GBM model, the most important feature was age. The rest of these, the age of the physician, the rest of these are all related to kind of how the notes are written, how orders are entered, and some other kind of customizing features that people have done in the EHR. And so overall, I think we're finding that we're able to predict physicians with the highest risk of burnout with modest accuracy. That's maybe being a little bit generous even. But it is an unobtrusive prediction model, which is using only data that are already collected routinely in the EHR. Age, notes, orders, and messages were kind of the categories of the most predictive features. But kind of looking towards the future, some more transparent measures, perhaps using raw audit logs or some kind of additional feature engineering may improve our ability to risk. So that was my quick snapshot, and I'm happy to answer questions, either now if we have time or offline.
Sorry, it's on mute. I guess really quickly, I'm curious. So the idea is this would be monitoring the physicians' use, how they use Epic, right? And like ethically, what is the response to that?
Yeah, so this is it's really kind of developed with the goal of identifying clinics that are at risk rather than individual physicians at risk, even though the training all kind of occurs at the physician level, the implementation of it will be at the clinic level, because it's really kind of trying to identify systems issues that are putting entire clinics at risk where the interventions would be at the clinic level. And then additionally, I think it's not trying to diagnose burnout. It's not trying to identify that somebody is burned out. It's really trying to, identify that they're in a situation that's putting them at risk for burnout. And so, yeah, we've had to be, I think, very careful about how we set it up in order to avoid sort of that, kind of, I don't know if anyone's seen Minority Report, like that Minority Report, like predicting something that, kind of makes people a little bit queasy because that's really not the goal of it, and that's not kind of what the implementation would focus on anyway.
Yeah, great, very interesting. Thank you. I will direct people to contact Dr. Tawfik offline if you have any additional questions. But we'll move on to being in Christian Rose next. So
hey there.
There you are. Dr. Christian Rose is an assistant professor of emergency medicine and a clinical informaticist specializing in the broad intersection of clinical medicine, informatics, and innovation, specifically in human-centered information systems and design. And he's bringing us today a presentation about context is key, unlocking new measures from EHR audit log data.
All right. Can you guys hear me and see my screen?
Yes.
This time?
Yes.
See.
Thanks.
Cool. All right. Hi, I'm Christian. I first just did want to say, like everyone else has been, how much I appreciate the STARR resources. And while this is one of the projects, there is another one even recently that I didn't have prepared for slides that involves a group of emergency visits at 5 different major sites across the country that the STARR group was really helpful in getting me data for to look at how patients are using their My Health app, and involves now over 1 million patient visits across sites like Mass General, Yale, University of Washington, Stanford. Someone else had mentioned we tend to be one of the smaller locations, but a lot of times our work winds up being pretty foundational because we have pretty well curated data sets that the STARR group has worked really hard on that make it so that we can share our knowledge with other multidisciplinary sites. So I've been fortunate enough to benefit from some of that work. And this work that I'm presenting on is a little bit of a different take on some of the information you can get from STARR Data. That was also a multi-site research project that involved UCSF and Kaiser Permanente, actually. So just to give you a brief agenda to talk today, we'll go over the background and talk a little bit about, we've heard a lot about clinical factors and proteomics, genomics, different omics, large language models, AI, etc. We're going to talk a little bit about trying to use these data resources to understand the context of the care environment, which as an emergency physician is really important to me. And then I'll show you how we did that and what some of the results that we found were. So just to put out to the audience, if you imagine what are some of the things that might affect outcomes for emergency patients, generally people think about clinical factors that we've talked about earlier today, like vital signs, age, sex, comorbidities, various omics, all of the stuff that we associate with clinical factors. But for a lot of providers, we also think about what are the contextual factors that affect care and health outcomes for our patients. Where did you present? What time of day? Was it 2 in the morning when everyone was sleeping and the cath lab had to be activated? Was the emergency department busy? Or how experienced is this location? There's a lot of conditions that obviously depend on people having experienced and timely intervention teams like STEMI here, trauma, acute stroke, or even sepsis. All of these require like teams who have trained very well and have all the resources necessary to provide definitive care, which ultimately improves outcomes. And rarely is that the case as much as in acute ischemic stroke, where we use the phrase time is brain. With every passing minute, millions of brain cells die. So we want to rush in the emergency department to try to get people a clot busting drug called TPA. In order to do that, though, you have to go through a ton of steps. This is Stanford's code stroke pathway. You have to get the patient registered, weighed for the medication. You have to perform labs, do an EKG, do an NIH stroke assessment by a neurologist. A radiologist has to read the CT scan. The emergency physician needs to make sure they're stabilized. All of that has to get done before you eventually push the clot busting drug and treat their acute condition. So it takes a lot of coordination, and obviously different things can affect how well you can do that. So when we talked with a group of experts, and this is an example of the emergency department during the COVID pandemic, their most important contextual factors they felt were busyness of the emergency department and experience. Like, how experienced is this team? Have they worked together before? Do they know how to predict each other's next moves? So how would we try to understand that? Just to think in terms of STARR and the resources available to us, we might try to understand the context of the care environment through clinical data. Obviously not patient generated, cost utilization, public health data is not going to help with this. So we need to look at clinical data, but specifically a subset of that clinical data called the audit log, which Dr. Taufik spoke a little bit about earlier. Which essentially is what every click and interaction providers of any sort have done in the electronic health record over the course of time. It's initially, just to give people background, it exists because of HIPAA and meaningful use requirements to ensure privacy for patients. And this is just an example of when I did my medical schooling at Columbia and New York. People lost their jobs because they were accessing Bill Clinton's heart attack health records, which was not cool. So what does that data look like? Again, people are familiar with vital signs and various other data, but the audit log is essentially just a prospective recording of a timestamp, a user ID or location ID, and an event that was performed. It's orders of magnitude larger than the general clinical data sets, but and can be very difficult to navigate because it's so granular, and then sometimes not granular enough, unfortunately. You can tell if someone reviewed notes, but you can't tell exactly necessarily where in the note they were looking or which type of note specifically someone looked at, but you can get all of the time series events in the hospital. Other key distinctions, if you're thinking about this for your research, are clinical data tends to be patient-centric. So, when did the patient come in? When did they visit in their presentation? What's their CSN for that encounter? What diagnoses, medications? The audit log is more user-centric and like institution-specific. It's just recording what everyone is doing at the EHR terminal while it's progressing. So it's just, again, a ticker going the whole time of everything anyone is doing at their computer terminals. And given the majority of work now being done by clinicians is at the computer terminal, you can imagine this is a lot of information, a lot of what we do. So much so that it's being used in a lot more research. Here's Dr. Taufik's paper with Dr. Pagalera as well. some really interesting work being done to better understand health systems, health services research, and like healthcare delivery through the audit log and how providers are interacting with the care environment. So all that's well and good, but how are we going to use the audit log, and how did we use the audit log then to understand variations in care at our institutions? Basically, you might think about what we just talked about with stroke, of the door to needle time, everything that needs to get done from when the patient comes in to when they get TPA. But since people do events and then they backlog them, we needed to include a little bit more of a treatment window. Sometimes things happen and we go back and say like, oh yeah, I delivered the medication at this time. So the audit log wouldn't know that because it's keeping a running list. So you have to leave room for some of these other events that may be back charted or timed differently. So something important to think about if you're trying to use the audit log data for research. It's not necessarily just the beginning and the end of these windows, but sometimes things happen a little bit later. So just going back to what that data would look like, okay, we've got user IDs, we've got event types and times. What are we going to do with that? So for our work, we basically we used first just STARR data to get a cohort of stroke patients, people aged 18 or over who had an acute ischemic stroke and were given the clot busting drug TPA. So that came from your usual clinical data. And then we used those encounters to go back into the audit log and say, okay, who is everyone who interacted with that patient when they came to the emergency department. So we were very agnostic to what someone's specific role would be, and instead say, who are all the people who interacted with this person along their journey from check-in through TPA delivery. So you can see from this diagram, we have our cohort on the left, we have the encounter, we synchronize the encounters and filter for all the ones that aren't relevant to our visit. And then some sites, as people talk about today, there are some minute details and differences between sites that might use OMOP or other data sources. Stanford doesn't record what someone's role is, whereas other places do. So I would have like attending emergency physician. That might not actually be recorded in STARR. So we'd try to understand who I was based on what interactions I did in the chart. Whereas another instance might have something like my specific role, nurse physician registration. But we linked all those people to identify who the care team was. And then we started to look at what elements of busyness and experience we could extract from all of the prior encounters those people had shared. So once you had the cohort of all the users who touched the patient's chart in that window of time and the treatment window, we could then look at things like how many unique workstations did a person visit during that ED encounter, which could be a proxy for how busy the ED physician was. Are they running to radiology and then coming back to the ED to treat other patients? How many total patients were they managing at that same time? And also like how many times were they switching between terminals? We then also looked back and said, how many times in the last 6 months had those people worked together on either strokes or any other medical case? And that way we were able to get some of these measurements of teamwork and busyness. And essentially that comes down to like a sort of network analysis with weighted edges determined by like how often people had worked together in the past. Just to give you an example, we only used 3 in our research, but there's a list of all the different ways we thought we could use the audit log to measure busyness in the emergency department. So tons of different ways to measure busyness or experience, and we just chose a select few that we thought were feasible over the 3 different sites that we were working across. For experience, we had different ones as well. Down here, the average team experience, sorry, there's busyness and experience metrics in here. I apologize for that. But basically, you could measure this in any of several different ways. You could, since it had not been done before, we could sort of choose our own metrics for what we thought was the best way to measure experience in the past. But all of these are valid and could be explored separately if you wanted to try to understand various versions of the context of care or the experience of team members. And ultimately, what we found, here are the 6 metrics we chose for our research that was published in JAMIA. For busyness, we chose how much someone was moving, how much team members were charting, and how much they were switching between charts. And ultimately, only one of the sites showed any statistical significance with time to TPA delivery from any of those busyness metrics, which actually is kind of helpful and correct in a way. We have code stroke pathways, so if those made a difference or if those were related to the delivery of TPA, they'd probably show you or tell you that your coach stroke system is not working. On the other hand, for teamwork, for the experience measures, the recency of a stroke didn't have any impact on how quickly TPA was delivered. But if people had worked together, or more specifically had worked together on delivering TPA more often in the last 6 months, they had faster and faster door to needle times, which was really both what we expected would be the case, but also important to see from this unique data source. We even then looked at that data and looked at the quartiles for like the number of experiences, and we did see a sort of dose response as well over the like Q1 to Q4. So important to also show that it does seem like there's some level of linear relationship. We'll just move on past future directions pretty quickly, but obviously we can start thinking about how we would want to build our teams and make sure that we have the most experienced team on the court or in the ED together. And we might also try to think of like how we should organize work and how we can make sure that people are doing initial parts of that care pathway in parallel so that they're not in each other's way. And we might even begin to use other models to look at, hey, what's all the work that needs to be done and who can be doing it faster, so you can start to cluster out like work based on not just roles, but more who can do what when in the care journey. So that's pretty much it. The audit log, as I said, offers a novel data source to help providers understand the context of care. We looked at busyness and experience, and it does seem that from our work, team experience is associated with faster door to needle times. So thank you all for listening. Feel free to email me at ccrose@stanford.edu. And thank you so much to Jonathan Chen, who's a super user, super member of the STARR and Stanford family. And I always appreciate his insight and work here. So yeah, thank you guys very much.
Great. Thanks so much, Christian. I know it's very late, but if you have questions, if you could send them along to Christian offline. And so we will take Louis right now, and he'll be our last speaker for today. And thank you everyone for hanging in there. So Louis Meichemeyer is a PhD student in the Department of Electrical Engineering. His current research focus is developing algorithms for chronic disease risk stratification and quantification of biomarkers from medical images. And he'll be sharing with us today about the simple framework for extracting diagnoses from clinical notes.
Yeah, thanks everyone, and thanks for hanging in there. Don't feel any pressure to stick around. Let me try to get this going. Let's see. Can you see my screen?
Yep.
Perfect. Yeah, so I'll be talking about a simple way to try to extract diagnoses from unstructured clinical notes. And this was worked on with a great group of people. And we just got a short paper accepted to ACL 2023 on this work. So our goal with this work was to identify patients with specific clinical outcomes and the timing of these outcomes. And we really wanted to do this because one of our projects is to take medical imaging data and also take electronic health records data and predict 5-year incidence of various chronic conditions. So here are 5, and we've also added several to this list. But this is, we found that you need to use like some source of labels for patients that have different outcomes. And one way to do that is to look at like ICD codes, diagnoses codes for finding these patients. But we found that often several of these conditions are undercoded. So we realized that we had to look kind of beyond this thin layer of structured data in the EHR to really figure out which patients have diseases and when they develop them. But it can be challenging to actually find the patients that develop these diseases, especially on the scale that we want to do this on, which is on the order of like 30,000 patients. So current methods that people use to do this are rule-based. Like you have some regular expressions that you just look through the notes with, or you can train neural networks that look for specific diseases in clinical notes. But the challenges for us with this were that they require a lot of manual effort, and they also have limited generalization. So if you train a neural network for one disease, it doesn't necessarily work on other diseases. And we wanted a method that was quick to get up and running and would work on a bunch of diseases right out of the box. So the method that we came up with, and this probably isn't the best way to do this, but this is what we tried. So we call our method HYDE, which stands for Hybrid Diagnosis Extractor. And our method, what it tries to do is it tries to integrate these labeling functions, so kind of rules that go through the EHR and try to find different mentions of diseases, with neural networks that are really good at understanding context and figuring out kind of which mentions of diseases actually indicate that a patient has a disease. So I'll go into the method in a bit more detail. But first, I'll talk a little bit about our data set that we're working with from STARR, and super grateful for the work that people at STARR have done. This has made this project and many others possible. But the data that we had was 8.8 million clinical notes from 23,000 adult patients. And the phenotypes that we're trying to understand are hypertension, diabetes, osteoporosis, chronic kidney disease, and ischemic heart disease. To do this, we extract something that we call mass contextual mentions. So these are mentions of a disease in a clinical note, as well as their context. And then we just mask out the mentions of the disease. And then these mass contextual mentions are passed into a fine-tuned biomedical language model to disambiguate a patient that where maybe the clinician is saying they don't have this disease, like they don't have hypertension, or they're saying the patient's father has hypertension, or they're saying they might have hypertension. So now I'll describe the method in a bit more detail. So first, in this first box, it shows that you can develop a simple labeling function to look for diseases that you're interested in. So if you're looking for diabetes, this might just be the regular expression diabetes or diabetic. And then the second step of the method is you apply the labeling function to your clinical notes. So you'll run this rules across the clinical notes. And in this kind of toy example, you see that diabetes is highlighted in green, which indicates that we found that mention. Also, we might have found a diabetic mention. And then you can also extract some terms in the context. So these terms in red are terms in the context that we can also extract. And then we also include in our mentions periphery terms, which is what we called them. But these are terms that often are associated with the diseases that we're interested in, and we want to mask those out as well. And really, the idea of masking out the mentions is to create, basically just create a representation of the context of the disease, but not include any kind of information that is disease specific. So then we can take these mass contextual mentions, which look like what's shown here in box C. So the first one would be like has and then mask in patients. The second one would be not and then mask. So clearly the first mass contextual mention should be a true positive, like the patient actually has it in that case. The second one, it's saying not and then the disease. So the neural network should say that it doesn't have that one. So yeah, when we pass those through the neural network, it should indicate those results. Yeah, and then the hope here is that we can do this for a bunch of different diseases. So we can develop labeling functions for whatever diseases you're interested in, and then you can just reuse the same neural network. And it should learn just to look at the context and be able to understand whether a patient actually has the disease or not. So we labeled these on a mass contextual mention level, and we labeled them as either true positive, false positive, kind of like a general false positive category. And then we also had more specific false positive categories. So one that indicates that the mention is referring to someone else, another one that says that the mention is negated, another one that indicates that the clinician is giving some instructions, and then another one for an uncertain category. And then we found that our mass contextual mentions sometimes had fewer examples from some of these categories. So we used regular expressions to amplify certain examples from some of these categories. And then we also used human in the loop, uncertainty-based active learning to iteratively label more examples that could be most useful for training our model. As our base biomedical language model, we used a PubMed BERT model, and we trained just on hypertension mentions. And then we evaluated the area under the precision recall curve and F1 scores. So this is a bit noisy, but I'll walk you through it. So if we focus on the table on the left, each row here corresponds to a different training data set makeup. RS stands for randomly sampled examples, and the model is trained on these random examples. When we add in the C, so like an RS plus C in the second row, that represents adding additional examples that are amplified from specific categories. And then A1 through A4 are just different iterations of our active learning. So if we focus on the bottom row, which is our best model, trained on the most data, we see that we get these values for AUPRCs. And in this first column, this is the hypertension value that we get, and this was the disease that was trained on. So we call this like supervised learning. And then all of the other diseases are diseases that were not trained on, and we just reuse the same neural network without additional training. So this is like a zero-shot evaluation of our neural network on these diseases, and we get similar performance. Sometimes you see that the performance is like better on the other diseases, and this is probably just because you have different balance of data, and AUPRC is sensitive to that. And then in the right table, we compared to a labeling function baseline, and we showed significant improvement of our method over just using labeling functions. So we did one more experiment where we looked at how many words in the context do you actually need to disambiguate these different mentions. And we found that a context length of like 16 words, so 8 words on either side of the mention, was like pretty good. And then when you go below that, you start to get some performance decline. And this was kind of the case for all the diseases. So that brings me to the end of my talk. And thanks to everyone in my lab. I'm Akshay's PhD student, and then worked also with Professor Nigam Shah and several others on this work. So yeah. So I guess I'll open it up for any questions.
I don't have any in the chat. I do encourage everybody to contact Lewis if you have any questions. I know it's late. So I will thank you, Lewis, and turn it over to Priya to close us out.
Yep. Thank you. Thank you, everybody, for sticking around. Lewis, that was actually a really interesting talk. You had given one last year that was as well. It was really exciting. So I was really happy to see you volunteer again.
Yeah, thank you so much.
Yeah, no, thank you, everyone, for the amazing work you've done, for attending the user group meeting, and this was a really informative afternoon, at least for me. I think a lot of the talks were really cool. So I will get around to posting the recordings. Give me a couple of weeks because we'll wait till the Atlas workshop is done next week, and then I'll post the recordings on the YouTube channel. But I won't keep you guys any longer. Thank you very much for staying. And with that, I think we should conclude the third user group meeting. So thanks, guys. Bye.
Thank you, Priya.
Bye, thank you.
Thanks.
The preceding program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.